So I thought in this video we'd look a little deeper into this H8-16 RAM card here. Right up front I'll say this card is different from the WH8-16, that's WH8-16. Found some information on Google Forums. It seems like the cards are similar, but some of the chip identifiers are different, which was interesting. I made a few notes here. On the WH8-16, it looks like these U140, etc. here are these parts, whereas on the H8-16, a couple of the parts are different. I'm suspecting design-wise it's very similar, if not the same. I've had a hard time finding a manual for the H8-16, but I found some selected pages that somebody had scanned for the WH8-16 and again posted on the Google forum. I think I've found a manual for the H8-16 and I've ordered it. Once I get the delivery in the mail of the printed out copy, we'll find out if I have the correct manual or not. But I think I kind of have enough here to understand the card, enough to be able to test deeper. This dip switch we see up here that I mucked around with before is interesting because in the configuration the card came, all four of these upper positions are to the right, or the disabled position, and then there's this switch 1 here, which is the board enable, and it turns out you can, with power on the board, move this to the disabled position. It'll keep it from writing to the card, but you'll still have the content stored on the card. So that position has to be to the left in order to actually write to the card. The other four positions on the dip switch are kind of interesting, and they're kind of captured here, and hopefully I'm getting this in frame. The switch positions are labeled 020, 040, 100, and 2001. It turns out combinations of these switches add up these addresses to set the origin address of the card. So if I wanted the card at origin address 040, I would put switch 3 on and the other switches off, these other 3 switches off, and that would be the origin address of the card. The card is delivered had them all off, and my guess is that setting the origin address to address 0. And we'll talk about that a little bit more here in a minute. The address decoding for the card, and this is not going to show up well here on screen, and I apologize. We have the dip switch that comes through, and we have the 4 switch positions that set those addresses that go into a binary adder, which is kind of interesting. And so it's comparing A12 through A15 to positions of those switches and doing an add, and the outputs of that add come into this device here, which looked like it's a 2 to 4 demux. Memory select feeds back in, so it seems to be this demux based on the output of this adder over here are being used to select where the ROM banks are at. So this already says to me that these 4 ROM banks have to be contiguous in memory. You can't independently set them one from the other. There's no surprise in that. The upper half of the adder is interesting because it's feeding this line out here that, if I can read that, this is not the best copy. As always, I'm going to complain about reading glasses. See if I can read that signal name. So the upper half of that adder and then the demux becomes address select out. So this is taking care essentially of selecting the address range of the card. So I'm guessing with all 4 of these switches open, which is the position I believe we're in. Are we on or off? We are off. These pins, all 4 of them get pulled up to these pull-up resistors high, and that maps ultimately the card into the lower origin address of the card at 0. At least I'm guessing that's what's going on here. That seems logical. So I think the next step in talking about this is to talk about the memory map on the H8 as I understand it, and why this card would be set at origin address 0 and not at, say, address 40, or yes, to be above the ROM. So let me set the card aside. And let's talk about the 8080 processor and memory map. So the HeathKit, as I understand it, as originally built, and I believe this is called the PAM monitor mode, I could be wrong about this, has at the bottom of memory. So I'm going to start bottom of memory here, and that is 0K. And this is ROM. And then above this is going to be some amount of RAM. So the ROM starts at address 0 on the address bus, and that's done because when the 8080 or the Z80, apologies for the horn outside, are reset, they go to address 0 in the address space. Oh, come on, what are you doing out there with the horn? And execute the first instruction at address 0. So it makes sense to have the ROM at the bottom of memory because that's where the reset vector becomes to start the system up. So this is, ROM starts at 0. There's 8K total of ROM here. And then the RAM will start, I believe, at the 8K boundary here and can extend up all the way to the end of the 64K address space. So depending on how much RAM you have, it may fill all the way up to the, like I say, the top of the available memory. That seems to be the core configuration. In reading, there's what they call the org0 modification, and I suspect, though I don't know it, that's what I have going on here. And so what that org0 modification looks like is, again, I have the 0K space here. I have ROM, trying to keep my hand out of the way, which is 8K of ROM. And then I have RAM sitting in parallel to this. So I have RAM that can go all the way up to 64K. Its origin is also 0K. And what looks to happen in this is what they call the org0 mode, is an interesting quirk of the hardware design, is if I have RAM and ROM where there's an 8K space that overlap this way, the address decoding and general decoding for the ROM and RAM will work this way. If I'm doing reads, it'll read the content of the ROM. However, if I do writes, it'll actually write into this RAM here, which is interesting. And so it looks like what this org0 modification does is the system powers up, it goes to address 0, the reset vector. It begins execution out of this ROM, and it looks like the ROM actually runs code that reads each byte out of itself and then writes it back to the same address. And what that does in effect is take each byte, the entire 8K space, and copy it into this lower 8K of RAM. Then it looks like something happens that disables this ROM for read and enables this lower 8K block of RAM for read. So the ROM is now off the address bus, and I am executing a copy of that ROM code out of RAM over here. So why would you want to do something like this? If you're looking at an operating system like CP/M, CP/M expects to have RAM. So if we go in here to 0K, it expects to have RAM starting at that bottom address of the machine. CP/M loads, I'll call it the kernel, that's not a good term, but loads the operating system into here. And typically in CP/M, and again I'm working in hex here, I believe it's address 0100. Becomes the typical program load point. So you've got Core I/O, whatever things you need in here. So to boot CP/M, you've got to be able to write in RAM through these addresses. The problem here is if we go back to the original memory map, we have ROM. Actually, I should have drawn that in green. Apologies for that. Stay consistent here. This is RAM 0K and that vector 4. So with CP/M expecting there to be RAM in this lower 8K space and finding ROM, CP/M just can't boot. So as I followed kind of what I've read on this org0 mod is a way of getting the system booted. We're reading from these addresses and copying the ROM across, disabling this ROM totally, and now executing out of this memory space. And with that, it could then find a floppy drive, bring CP/M in, bring the CP/M code that it needs to into this bottom address space in RAM, and CP/M can go along its merry way, as this is a flat RAM address space. So I'm talking through all this to get back to this card and why I think it's strapped with its origin at address 0. You may have saw me in the previous video go in and set these switches to various places, and instantly the system would fail. It wouldn't even start up without the 4 switches set to 0. And I believe that's because if I take this card where we need it to be in this configuration, and I make the origin of the ROM or the RAM anything less than 0, what actually happens on the machine looks like this. So we have that ROM 0K to 8K, and say I've set the RAM origin address to be this 8K boundary. So I'm guessing what happens is the system powers up, the reset vector occurs, the machine begins execution out of the ROM, and it goes in and tries to do this copy where it takes byte 0 here and tries to copy into what it believes is RAM here, byte 0, and transfers the 8K across, then does the bit of work that disables this ROM off the bus, and then tries to execute out of the space here. Well, there's no memory, so the machine just crashes. So I'm guessing really that's why this RAM card origin is set to 0K along with the ROM set at 0K. Hopefully that made a bit of sense. This bit of reading has led me to how I'm going to investigate this card. Oh, lots of paper here. So assuming this card is configured the way I've just said, where the card, getting the color code backwards, I'd like to keep what I'm drawing consistent. Assuming I have this correct, this is going to come up, in this case, to a hard boundary. That's only a 16K card. So I've got a 16K RAM space here with origin again at 0K to 16K at the top. Assuming I have this right, the system wakes up, it copies the ROM most likely into what's labeled bank 0. I think this is labeled on the card bank 0. Oh, maybe it's not. I don't see an actual silk screen that says bank 0 to 4. Anyhow, this RAM card is actually configured because these are, this is getting interesting. These are 4K by 1 RAMs. This card's actually organized like this. So again, we're going to have 0K at the origin. We're going to have a 4K boundary, an 8K boundary, a 12K boundary, and a 16K boundary at the top of memory. So one of these banks is going to represent this 4K. Again, these are all RAM. So one of these banks is going to represent that bank. One of them is going to represent. So the board is divided up into 4K blocks to get to the full 16K, because there's 4K of storage here. You know, these are each 4K by 1, and there's 8 of them to get that 4K by 8 bank select. So I don't know which one of these banks has the bad RAM. Actually, I think took some notes. So what we saw when I powered the system up was a flaky address at 012. Boy, I don't remember now. Was that? That'd be the least significant byte. Let me take a peek at the system here and just make sure I'm remembering the address space right. Of course, without the RAM card installed, it won't power up. So apologies for being off camera here. Let me install this RAM card and just make sure the behavior is what I think it was. The card's in correctly. System's powered up. Let me go to address. See, 000,000, and just start reading. And I'm seeing what appear to be solid reads here. I believe 0, so address 0400. That's where we get to those weird bytes were. Yep. So that's how I remember it. So this is an octal 040012. Remember, it's a split octal address space. 023 and 033. Oops. We saw that weird behavior at these addresses where the data just toggled around and went really crazy. So if I break this out, 00100 000 000 001 010, and these bits here will stay the same. This is the, actually I do that really poor. This is the this is going to be A8 to A15. Actually, let me draw it this way: A15 to A8, where this is A15 to A8. This is going to be A7 through A0. Again, A7654 all the way down to A0. And there's a 000 010 011 here. And there's a 000 011 011 here. So in this case, the bank is in this split octal is the 040 bank. Now I need to do a little bit of a calculation in my head to figure out which one of these banks that would be. Boy. It's translating from octal to hex. It's kind of weird. So we have 0, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. I'm just writing in column weights. So this to me So I've got a full 4K there. So it would be, boy, I'm going to have to go off and jump on a calculator here. It's not clicking in my head how these map across here. The octal's really throwing me. So to have 4K total addresses, it'd be that group of bits, and that should be 12, 3, 6, 9, 12. Is that right? 13. These 4 bits up here, that's a really poor 0 written there, represent 4K blocks. So these bits up here represent 4K blocks. And I say that because 0000, 4 bits here, can represent 0 to 16. And 16 times 4 is 64K. So these 4 bits here are the address select of 4K blocks. So with 14, this is A13, and this is probably not readable. So if we take A13 and A12, if they're set to 00, it's going to be this block. 01, it's going to be this block. Write it correctly. 10, it's going to be, yeah, I'm writing this rather poorly. 10 is going to represent this block, and 11 is going to represent this block. So because we're seeing a 01 here, it tells me that the RAM bank is bad is most likely this RAM bank. So again, with these 4, with A15 to A12, all zeros, we're seeing this 4K. With a 0001, we're seeing this 4K. A 0010, we're seeing this 4K. And a 0011, we're seeing this 4K. And that gets us to a 16K address space. And then A15 and 14 here are 2 bits, so there's 4 combinations. So 4 times 16K gets us all the way to 64K. So I'm confident what I've essentially drawn out here is good. So that RAM block is suspect. Think a little bit about the selects on these RAM blocks. Looking at the schematic, there's not a lot of, there's a data bus coming in. So I can see this is bank select 0, this is bank select 1, bank select 2, bank select 3. If we take bank select 2, trace that around again, it appears to go to U120 to 127. On this board, U120 to 127 is this bank here. So I'm guessing we've got an issue with this bank of memory. But that assumes this H8-16. These numbers are identical to the numbers on here. We don't know that for sure. I'm also guessing that because the ROM monitor is working, RAM down here is probably somewhat okay. There's enough RAM that's working that when the monitor ROM gets copied over and executed, the system can run. I don't remember offhand. Oh, that's curious. I could be mistaken here with this. I don't remember where the stack gets located. These bytes I'm seeing randomly change could be part of the stack on the system. That could be, and they're supposed to be changing because the ROM monitor is using those as working storage for stack or other things to drive the system. So this weird behavior I'm seeing with those bits acting flaky may not be indicative of bad RAM. So I don't know if that made any sense or not. But we'll talk about that as well. So we've got the system in a boot state where we've got our 4K blocks of RAM, the ROM, which is an 8K, has been copied to the RAM. And 16K has been copied to the RAM. The ROM is off the bus. The monitor is now running here. In the 8080 and the Z80, there's a register called SP. That's the stack pointer. The stack pointer is a scratch pad area in RAM where the processor can push things onto that stack and then pop them back off when it needs them. So if it does essentially like a function call, you can push the state of the machine, the registers, onto that stack, execute that function, and then when you return from it, you can pull the register values back into the registers from that working stack. It's a place basically in RAM where the processor can save state, potentially have variable stuff like that. And when you initialize the system, you set the top of the stack pointer to an address someplace. So if that top of that stack pointer was here where there's no RAM up to the 64K boundary, the system wouldn't run because it would be trying to use memory that doesn't exist for the stack. So the stack has to live someplace, most likely in this 8K space. I think the system's designed by default for there to be 4K of memory, which means I think in the minimum configuration, this space here is the RAM space. And that would say the stack for the monitor has to live someplace in that address space. Now, I don't know this. If I had written it, and I believe with the stack pointer, you set it to the top of the stack, and then the stack grows down through RAM in there. Don't quote me on that. I validate it. But I'm pretty sure the system initializes, it sets the stack pointer up here to the top of this 4K space. The stack is growing down this way. So this is stack. A user program is growing this way. Let's see, that's 0400. So we have 0000 here, 0010 here, 00. Let me write this all the way out. 00. No, that's not right. 0010 000 here, and 0011 0000 here. So when the machine first comes up and you set the working address to be 040000, there's the 040, and of course we're setting the other 8 address bits here. So that's 040000 in octal. So when I go in and set the place to start loading a user program in, we set the address to 040000, which is this boundary right here, and we enter the opcode into that address, and the address increments up, and we write the next, instruction, the next instruction, etc. up. As we add those in, that address moves up through, so the user program is being loaded from that address boundary up. The system stack is up here high coming down. And I'm going to say because of how low these addresses are, they're very low down in this space. Down in here, with they're well within that first really 64 bytes in this space, that this probably isn't the stack making that noise. I haven't tried to actually enter a program and see if it'll execute. I doubt it will. I'm guessing the stack is starting up here and working its way down. Anyhow, that's kind of the thought process I've gotten through as I've worked through this. Oops, I'm dropping stuff. I'm debating whether to go in and swap the two banks that I think are suspect here. Take this bank and just swap the memory. And if I see that weird behavior where the bits are changing, move to a different bank, then I know it's got something to do with those RAMs. There's a few other oddities in this that make this kind of weird to decode, the issue. Because, from 040000 up to 011, the RAM seems solid. I can write to it and read to it and get a solid value back. And then this byte goes bad, and then there's good RAM in between, and this byte goes bad. That tends to say to me the issue isn't necessarily the select, for a bank, because I'd expect the entire bank to be kind of flaky. There's not a common, we looked at this earlier, there's not a common address here to this. There's really not, even though it appears A9 here, actually that's A0 here, or A1. It's common. The problem is it's also common on the bytes in between the work, and that kind of leads me to the thought process that it's not a decoding issue, but something weird in the bank of memory. On the flip side of that, what's weird is that it's random bits. What I need to do next is go to address 05. So yeah, this is what I need to do next. So we've kind of walked through this and said we believe this bank here is bad. It's starting at that 040 boundary. And the 06 boundary will start here. If I go to 060 and I see flaky behavior in there as well, that could make some logical sense. And that there's two 7805 voltage regulators. One seems to power this bank and one appears to power this bank. Is that necessarily true? And if one of these regulators has got an issue, there's noise on it, one of the tantalum caps is failing and injecting noise, it could be that one bank that's fed off one of these regulators is seeing issues just due to power supply noise, ripple, tantalum causing issues. That could potentially be. So I can see here the grounds are common as they should be to everybody. The +5 out is these two up here. So there's a +5 rail that runs to here and to here, and there's a +5 rail there that supplies power to the logic. And potentially to only one bank. There may be 3 banks here that have common power. Oh, it's hard to say without looking in detail. It may be one of these is powering these 2 banks and one is powering these 2 banks. It may not be split as cleanly as I think it is. And that would really be get in there with the ohm meter and look at the power rails. Again, it's kind of hard to reverse engineer this without confidence in a schematic. Just looking grossly at these, there appears to be a power rail on pin 18 and on pin 9. I'm going to assume pin 9 is ground, and it should be common to everything, including the TTL logic, and it is, all the way to the grounds down here. That makes sense. This pin 18 is power, VCC. So this is telling me that this bank and this bank, these derive power from one regulator, and this bank and this bank derive power from the other regulator. And we can kind of prove that through by getting on the regulator output. If I can touch it, and we see that regulator supplying power to these two rows, and we see this regulator supplying power to those two rows. So it's interesting how they've done this, that the one regulator feeds a set of rows and the bottom one feeds those. I'm sure that makes sense to some point. What I don't know is if this is, bank 0123 or bank 0123. It's kind of hard to say without doing a little bit more digging. But we're making some progress here. We understand kind of the power distribution. That's good to know. It may be worth dragging the scope out and actually getting on the two different power rails from the regulators and just looking at the two and see if one is excessively noisy. I think we measured the voltages grossly, and they were both just under 5 volts, which is typical and normal. Anyhow, I think I'm going to wrap this bit of video up here. We've done enough lecture, and I'll do some more reading and looking at the schematic and trying to determine how the banks are selected, and we'll go from there. So I'm going to wrap this segment up here. This is going to be a multi-part set of videos as we go through each board and figure various parts out. Anyhow, we'll talk soon.